I'd like to see if I can describe to you how you could measure the bond energies of complex molecules. And to start out, let me just say that, let me remind you what we're talking about. Let me talk about something like methane. I'm going to need a larger stick. If you have methane and you want to measure the bond energy, I literally want to reach in and measure the energy it would take to grab that hydrogen and literally just rip it out of there. And when you can see it does that, the molecule is going to have a change from a tetrahedral geometry to a flat geometry. And there's a potential curve that I've written as a Morse oscillator. And there's a 0-point energy. And you're going to have to measure the energy to go from the ground state up to the dissociation limit. I thought I'd try to tell you just in a simple way. If you took a molecule and you'd like to try to see if you could measure the different bonds in a molecule, how could the specific bond energies be measured? And let me consider something like methanol. I'd like to take methanol and I'd like to show you how you measure the bond energy to break the OH bond, then how you'd break the CH bond, or how you'd break the CO bond. And I don't want to calculate this, I actually want to measure it. All right, so one way you can do this is to use a gas phase acidity electronegativity cycle. This is a negative ion cycle that you'll take this molecule, say methanol, and if you treat this with a base such as it's fluoride ion, fluoride ion is actually going to attack the methanol, and when it does this, it's going to pull a proton off, and if it does that, you'll form methoxide ion. The fluoride ion will never pull the proton off off the carbon, because the negative ion that you get has the electron sitting on the carbon, and the oxygen is more electronegative, so you'll always get the top ion. And so if you could do that, what you'd like to think about is how could I measure an equilibrium between these two species? And if I have the equilibrium, I can get the enthalpy, and if I can get the enthalpy, I can get the acidity of this. So this is an experiment that a bunch of us do in Boulder. The world's expert in these gas phase acidity measurements is my colleague, Ronnie Bierbaum, Professor Dr. Veronica Marie Bierbaum, and she's very good at this. They have a flow tube, and what they do is, this is the experiment you want to do. So you would like to measure the reaction of fluoride ion pulling a proton off methanol to get the methoxide ion. So what you do is you have to, here, you can't get a lecture bottle of fluoride ion because they're charged. So what you got to do is take a gas and you make a plasma. You boil electrons off a filament, and as the electrons interact with the HF, the electrons get captured into a sigma star orbital, and the molecule detonates and gives you F- and hydrogen atoms. So the hydrogen atoms are injected, or the fluoride ions are injected into this flow tube. And there's methanol in here. And what happens is, as the reaction proceeds, the methanol has a proton removed from it, and you're literally watching the end of the flow tube with a quadrupole mass spec. The quadrupole mass spec monitors the negative ions that have M/Z31, and you'll watch them growing in. So as you watch the methoxide ion growing in, you can measure the rate constant, K1, that goes this way. So if you do that, what you're after is the equilibrium constant. So you got to get the equilibrium constant. One way to do this is that you would measure the reverse rate. So if you did that to measure such a reaction, now you turn the reaction, you do the reverse of this. You now have to make a vapor of methoxide anions. An easy way to do this is to have electrons interact with methyl nitrite. The methyl nitrite then disintegrates and it forms methoxide anion and nitric oxide, NO. And the methoxide ion then goes down the flow tube. And as the methoxide ion interacts with the HF, now what you'll see is F minus growing in. And you know it's F minus because Jesus only made a finite number of ions that have M over Z19, and fluoride is it. There's no other. So it turns out when you do that, you're able to monitor this. So if you've measured K1 and you've measured K minus 1, that is going to give you the equilibrium constant. And this is the difference in acidity between methanol and HF. But the acidity of HF is well known. It's 370 0.424 kcal per mole with this uncertainty. And so it turns out that these two numbers gives you the equilibrium constant, and this is going to give you the gas phase acidity. So by measuring the equilibrium constant, Professor Bierbaum has measured the acidity of this species. The way to think about this now, to use the acidity, here's what the gas phase acidity is. Remember, she really has this number in the gas phase. You know, in the gas phase, these molecules are never going to dissociate into ions because you got to deal with Coulomb's law. So you're talking about maybe 300, 400 kcal per mole. So it's a whopping amount of energy. So the way to think about this is to get that ion, you have to break the OH bond. Then you have to, then you have to somehow measure the electron affinity. That gives you the energy of the negative ion here, and the ionization energy of a hydrogen atom is how you get the proton. And here, this is the easiest way I think about this. That's this acidity. You want to get those ions. The first thing you got to do is reach in with a pair of scissors and cut this bond. So you got to pay that energy. You also got to give me the ionization energy of hydrogen atom. You got to pay me that, and because that gives you the proton. And then you take the electron and put it back on the alkoxy radical, and that's the electron affinity. So it turns out here. This is what we're after. We want this bond energy, and this will be the energy for that bond only. So the electron affinity for hydrogen atom is known to some pornographic detail. You couldn't imagine what's been done to this poor atom. This is known to like 80 digits. So it turns out, so the only thing you got to do is you now have to measure the electron affinity of the radical. All right. So how are you going to do that? This is an experiment that's done in, actually here by Mark Johnson, Professor Mark Johnson at Yale University, and it's done a bit by people in Boulder, Colorado. Here's what you do. You literally take a vapor of these negative ions, and if you take a vapor of the negative ions, you make a fast beam. You cross this with a laser. I know the energy of the laser precisely. So what you do is when the laser interacts with the negative ions, you'll eject electrons, and you catch them in a hemispherical analyzer, and you literally measure the kinetic energy. So this is the kinetic energy. So here, this is easy. If you know what the energy going in is, and you know what the energy coming out is, you've measured those two things, then the difference is the binding energy. So here's the negative ion. When the electromagnetic wave comes blazing in and strikes it, what happens is that here's the laser energy. So the molecule literally interacts with the laser, and an electron's knocked off. And what you're going to do is you're going to measure the red arrow. This is the kinetic energy of the photoelectron. So if you've measured what comes out, then the difference is the binding energy. So it turns out that this is the essential experiment you have to do. There's a bunch of details you got to pay attention to. If the product radical is vibrating, then the photoelectron kinetic energy will be smaller than the measured binding energy. And here, these are just a bunch of words. Let me just show you what you do. This is it. You make a, here, what, this is, Jesus, we did this like 30 years ago. Christ, I'm an old guy. When you do this, what you do is you take right here. So what you're going to do is you're going to measure the kinetic energy of the electrons coming out. So we're making a plot of the photoelectron kinetic energy. here, let me just show the laser is at is 488. It's a beautiful robin's egg blue, extremely bright laser. And 488 nanometers is 2.540 electron volts. So here, think about this. This is the photoelectron kinetic energy of electrons coming out. No electrons can come out with more than 2.54 EV, because that's all I got to put in. So the first time you see electron counts, this is electron counts, is at about 1 EV. When you actually measure it, it's measured to be 0.968 EV. And so the way you get the electron affinity is if you put 2.54 EV in and you measure 0.968 coming out, then the difference is 1.572, plus or minus 4 millielectron volts. And that's how you do it. This is detachment to the ground state of the methoxy dot. This is one vibration in the methoxy dot. This is 2 vibrations. This is 3 vibrations. Can you see how cool this is? You can actually take a vibrational spectrum. You're looking at the vibrations in a radical. Well, that's not hard. That's not easy to do because you don't have a lecture bottle of radicals. So this is a very powerful experiment on the one day of the month when it works. I'll not kid you. These experiments are Professor Beerbaum's. You spend most of your time with the hardware trying to make certain the electronics is stable and whatnot. And then when you're running, these people basically are dancing around the machine nude with tambourines, just trying to keep the machine stable long enough to get a spectrum. But when it works, you're going to get a number very clean. And you see how precise this is? I mean, this is a very nice measurement. So now we can now do what we're going to do. If Beerbaum has the acidity, and you know the electron affinity, and you know the ionization energy of hydrogen atom. So here are these numbers. When you put these things in, you get out that the bond energy is about 105 kcal per mole. And this is the bond energy of methanol in intergalactic space with nobody else around. And all of these people who like to think they can calculate everything by using all these quantum mechanical programs, now this is the number they have to get. There's no place to hide. This is a cleanly measured value. No experimental system is perfect. So for example, so problems you can have. I just showed you how to measure the OH bond. Suppose you want to measure the CH bond. Well, this will never work because for the negative ion cycle will never work. Why? Because when you take any base that you apply to this, the base is always going to take off the most acidic proton. Well, the most acidic proton is one off the OH because you get the negative ion with the electron on the oxygen. That's good. If you have a base that you try to pull a proton off the carbon, you're now going to put the electron is going to be on the carbon atom, and that's bad. Oxygen's more electronegative. It'll hold it much tighter. So it turns out the negative ions are not going to be a useful way to do this. And of course, if you were going to apply the negative ion cycle, then you'd have to measure the acidity of the negative of this proton. Then we'd have to measure the electron affinity of this radical. Does everybody see that this radical, this is hydroxymethyl radical, is different than methoxy? Because the dot sits on the carbon, not on the oxygen, so it's a different radical. So if you can't make the ion, then we can't do our measurements and we're dead. Not to worry. There's other techniques you can do. My friend David Goodman does radical kinetics. And so a thing you can do is you can make chlorine atoms. And when you make chlorine atoms and in a flow tube, he uses photoionization mass spec to monitor the products. And so he can measure K1 and he can measure K minus 1. So he gets the equal.
Can you explain what a flow tube is?
Flow tube is a beautiful device that's a meter long. It's my fist, 10 centimeters in diameter. And Beerbaum has flowing through this a tremendous flow of helium gas. And so when you make ions, the ions are made up here in the discharge, and then they're little.
What's the pressure in there?
The pressure will be about a torr. And so it turns out that it's mostly helium, and you have a few millitorr of the reagents that you've got. You You have a quadrupole mass spec. The quadrupole mass spec, of course, can't operate in a millitorr, so there's some clever pumping that you have to sample the output of the flow tube. And so the quadrupole mass spec only looks at the ions. So if you have a reaction that occurs in here, one ion would go away and another one would come up. And you can monitor this with a quadrupole mass spec. Remember, the way the ions get downstream is they're carried along by the helium. So that, and what's true in a flow tube is the distance equals the rate times the time. So if you have a shorter distance, you have a shorter reaction time. If you have a longer distance, you have a longer reaction time. And if you measure that variation, you can get a rate constant.
How do you change the distance?
It turns out that you can change the distance by admitting your reagent through a tiny little tube. And this tube is the cutest little thing you ever saw in your life. It slides on a little wire, and they literally, like a gorilla, they'll set the flow tube, they'll set the injection tube at a certain space, and then what they'll do is they'll systematically vary this by just by simply pulling this back. Then they'll measure the ratios of these rates.
And we talked earlier about Robert Hooke making a vacuum pump to
Oh.
lower pressure. So is that the kind? Do you have somebody down?
No, no. It turns out. Sure. Okay. So the Professor Bierbaum uses a set of pumps which are as big as I am. They're Roots blowers. These pumps will pump just a staggering quantity of gas, like 500 liters a second at this pressure. These pumps, I'm just telling you words. One of the uses of these pumps are to pump grain in grain elevators in Kansas. You ever been to some dreadful place like Kansas? I mean, there's 10,000 of these silos, and so the grain is pumped around in these with these huge pumps. So she has 2 of these in the basement. So it's a very hard experiment to do. So you can also do radicals in this, and let me just tell you Gutmann's experiment. He's going to measure K, E, Q, U, Y, and so he's going to measure the reaction from the equilibrium constant, from the temperature variation of the equilibrium constant. He's going to get the reaction energy of this, and the reaction energy of this radical reaction is you're going to have to pay the bond energy of this CH bond energy, and you're going to get the bond energy of HCl back. I now have to tell you something. The bond energy for HCl is known to be 103 kcal per mole. Remember, I told you the bond energy for methanol is 104. So the chloride atoms, if they hit the hydrogen on the end, on the OH group, if they hit it, they'll just bounce off because they don't have enough energy to do this. So they're only going to pull a bond, the carbon off the hydrogens off the methyl group. So when you do that, if you do the analysis, you can get that the CH bond on methanol is 96 kcal per mole. And on the days when it works, you can get this very precisely. So those are 2 of the bond energies that you can get from methanol. So you might wonder, what's the CO bond in methanol? In other words, you're literally going to take the methanol molecule and you'll karate chop it in the center, and you just want to cut it in 2. So that means I've got to measure the energy of the methyl radicals and hydroxyl radicals. So it turns out this is a straightforward thing to do. Turns out that if you want to look at this, that this bond energy is to get the heat from here. I need to get methyl radical. So to get methyl radical, you actually have to measure the bond energy of methane, because the bond energy of methane is the heat of formation of methyl radicals, heat of formation of hydrogen minus that of methane. So photoionization mass spec or reaction kinetics both measure the bond energy of methane to be 104.99 kcal per mole. The bond energy of hydrogen H atom comes from the dissociation energy of H2. So there's classical tables. These guys, Mr. Pedley and his friends, there's 3,000 of these bond energies that these guys anally have put in this book. So it turns out that if you have these guys, you now use the heat of formation of methyl radical I also need to tell you that the bond energy of water gives you the heat of formation of methyl radical, of hydroxyl radical. So it turns out if I know hydroxyl radical and I know methyl radical, then Pedley et al. Will give you the heat of formation of methanol. So this is the other thing I'm going to need. So it turns out that this bond energy is equal to heat of formation of methyl radical plus OH radical minus that of methanol. And so this comes from water, that comes from the bond energy of methane, dissociation of methane, and this is Mr. Pedley. And so that's actually the weakest bond in the molecule. The weakest bond in the molecule is the CO bond. So you can work all of three of these bonds out by going through a procedure. Me and a whole bunch of other really smart people have measured a large number of these molecules, and these are the bond energies. There's all sorts of complicated heats of formation that you can use. Let me just talk here at the end for the last part of this about trying to compare these things. One of Professor McBride's typically going on like a broken record. We always tries to say, how do you know what you've done? Which means to say, here, I'm not kidding you, it is very easy to make a mistake. If you get any of these calibrations wrong or any of these little cycles are done in an incorrect manner, it's very easy for you to have an uncertainty. Indeed, let me go back and I need to make one point I wasn't smart enough to do. Where I have this acidity here. This bond energy that we're going to measure, okay, we're going to get this through a cycle, and to do this cycle, we have to do two difficult experiments. Beerbaum has to measure the acidity. That's a very large number. That's 380 kcal per mole. And the electron affinity is known, but then the ionization energy of hydrogen atoms is known, but you have to measure the electron affinity for this radical. So this number, it comes from a cycle where you're adding and subtracting large numbers. And you're smart guys, you know this. If you have a number that you're after and there's a cycle that you go through and you're taking differences of large numbers, any fault, any mistake that's made here is going to be, that error is going to be in this bond energy, or any error that comes in this measurement. There's a famous chemist who's English, whose name is Coulson, and Coulson used to say, procedure is like weighing a captain on a ship by weighing the ship with and without the captain. Here, so you have an aircraft carrier. Okay, you're a smart guy. You get a pair of scales, and now you have to measure this aircraft carrier, the weight of this very precisely, and then you put a little guy on top, and then the weight's going to change just a titch, and your measurements have to be so precise you can pick this up. So on the days when it works, you can really get these bond energies, but these are not easy experiments to do. Let me talk here about these bond energies. Here, we've done several of these things. You might guess that if you have an alcohol, I did methanol. This is the OH bond in methanol. You might hope that the OH bond in ethanol would be the same, and it's exactly the same within our uncertainty. If you go to, this is isopropyl alcohol, or this is T-butyl alcohol. T-butyl alcohol is a little bit larger, but you can see amongst friends, it's all about 104 or 105 kcal per mole. When you go to measure something like phenol, this is an OH bond in phenol, but this is only like 86 kcal per mole. And you go, Christ, what's wrong here? Well, this is no regular alcohol. Here, I drew this. If you break the bond in methanol, you get a hydrogen atom and you get a methoxy dot, and the dot is stuck on the oxygen atom. But if you pull a proton off phenol, now the dot is not on the oxygen. It's actually delocalized around. It interacts with the pi system. And McBride's probably drawn you some of these resonance forms, or you can talk about the interaction of this extra electron with the pi cloud. This is a catastrophic change. What this is like 20 kcal per mole, that's a volt. So it's a lot easier for you to remove a hydrogen atom from phenol than it is from any alcohol. We've also done a bunch of peroxides here. Remember, here's hydrogen peroxide, here's methyl hydroperoxide, here's ethyl hydroperoxide. These again look like OH bonds. Here, you're also smart people. You know that these peroxides, they're very reactive compounds. The reason my daughter's a blonde is because of this. I mean, you can buy a bottle of this and only here, let's see. There's a difference between chemistry and, say, other subjects in that these molecules are real. When we go to do this, here, my daughter would get, you can buy a bottle of peroxide in the pharmacy for like, it's 5%. So it's 5% hydrogen peroxide and 95% water. So we have to make a beam of these things. So there's clever ways that if you can have these compounds and you can actually distill them, and you can make 99% hydrogen peroxide. The hydrogen peroxide, of course, is extremely reactive. Why is it reactive? It's because the two oxygens are held together by a single bond, and you have all these electrons that are crammed right on top of each other. So the bond energy of the OO bond is actually quite weak. So it's a very good oxidizer. So it turns out we had a bottle of about 99% of this stuff, and I'm talking to this with my students, and I'm not very skillful. And so it turns out you maybe had about half a milliliter of this. As long as hydrogen peroxide's in glass or plastic, it's fine. Nothing's going to happen. You can handle it safely, but it'll oxidize any carbon that it gets to. So alas, I dropped it, and when I dropped it, it bounced once on the floor, and then it broke. And when it broke, when the glass came down and it broke, it went foof, and there's a big orange spot around. And what happened was all the dirt and stuff on the floor is oxidized immediately, just gone. Okay, so if you have a solution of here, you think I'm kidding. You have 100% solution of something like this. You take the little bunny rabbit with the ears and sort of lower this thing in. This thing is just simply torn to pieces. Then you pull this thing out. There's just bones. I mean, this is tremendous. This is tremendously reactive. So all of these things, you have to handle them, and you've got to get them into your spectrometer. But when you do this, you see the OH bonds here. See the dots here on this is like, this is 88 kcal per mole. This is a lot different than these guys. And of course, the one that you're really interested in is water. Okay, the bond energy for water is 118, and that goes to OH dot and H atom. This is an important number. Remember, water covers 70% of the Earth's surface. Here, if you're making a list of what are the most stable compounds that God made, it's N2 in the air. 80% of the air we're breathing is N2. N2 has got a triple bond. It's indestructible. Very, very stable. The sand on beaches, I mean, the silicon dioxide, the sand is like a rock. I mean, it is a rock. And then the other thing is water. 70% of the Earth's surface. And the reason it's so stable is if you want to break this apart to radicals, you got to give me 118 kcal per mole. That's a whopping amount of energy here. And so you notice, if you just replace this with, say, an ethyl group, okay, so you make ethanol. So the bond energy is going to drop by almost a volt to 104 kcal per mole. Here, imagine you have a swimming pool. Here, so there's a swimming pool. Johnny Depp is talking to somebody next to the swimming pool. Well, instead of the swimming pool, you have water. You have ethanol. It's vodka in there. So Johnny Depp takes a drag and a cigarette, and as he's talking to Angela Jolie, he flicks the thing over, and the split second this hits the pool, there's a flame like 180 meters high because the ethanol ignites. It burns. Okay, if it's in water, the cigarette goes out. So this bond energy, if it's a real stable compound, this has consequences. Okay, so the last thing I'll tell you is these are the bond energies I just told you for methanol. This is the OH bond. This is the CH bond. The weakest bond is the CO bond. These are these numbers in kcal per mole. It's always interesting if you knew what these bond energies are. What are the bond energies for the radicals? So if I reach in and cut a bond here and I make methoxy dot, if I make methoxy dot, now the bond energy here for the CH bond, here I can use the meter stick, the CH bond, which used to be 96 kcal per mole, drops to 22. You can see why. The minute you cut the bond here, the hydrogen atom leaves, but this dot couples with that dot, and you got formaldehyde. Nice, stable compound. So, and the CO bond here is about 90 kcal per mole. This is about the same thing for the CO bond in methanol. You go to the other bond, which is hydroxymethyl. You go to this species. Again, if you cut the bond of the OH bond, you get a dot here, and the other dot then combines back here as formaldehyde. So now this is 30 kcal per mole, is to be contrasted with 106. What's interesting is the CO bond, which used to be 92, goes up. I don't know why, but it does. And not by a little bit. This is almost a volt. So there's all sorts of interesting patterns you can have in these bond energies, and you literally can have you can look at not only these alcohols, but all sorts of alkyl peroxides and a variety of these things. Okay, here, I'm going to finish early, you can see. All right. All right, so here, there's another thing I want to show you, and that is when you talk about what a bond strength is, it turns out that an early way that people tried to measure bond strengths would be that you'd consider a molecule like methane. I need my big stick here. And you take methane, you can burn it, and you can actually measure the energy to take this apart to a carbon atom and 4 hydrogens. So he told you that Chupka described to you how you would measure the energies of individual carbon atoms. You can actually work out that the bond that this is to break all 4 bonds in methane. It's going to cost you 497.5 kcal per mole. And since there's 4 bonds in methanes, you'd cross yourself, think of Jesus, and then just divide by 4. And if you did that, that number divided by 4 is 99 kcal per mole. Okay? And so you'd figure that must be sort of the average bond energy. If you go through these cycles, like I just told you, you can actually measure individually. The first bond is 104.99 plus or minus 0.03 kcal per mole. And that's the first bond energy. That gives you the absolute heat of formation of the methyl radical. You can now take methyl radical and measure the second bond. Notice the bond energy goes up from 105 to 110. Then the third one is 101, and the last one is 90 kcal per mole. And these guys give you individually the heats of formation of all of these species. Notice that not a single one of these bond energies equals that average. Here, it's close, but the uncertainties are such that it's not quite. And so using these average bond energies, you got to be careful. The other thing that I'll also tell you is if you actually take the sum of these numbers and add them up, it's 397.5. It's exactly this. And this is a testament to the guys who did these measurements. These are very hard experiments to do, and that means that each one of these 4 numbers is right, because you know this thing has to be right. The 4 of these guys have to add to these things. So here, the sum of these things is this. That means the first law of thermodynamics really works. So this is a very interesting set of experiments to do. Okay, so here I'm going to give you people. Okay, so I'm allowed to show my last little picture then? Okay, here. This is, I'm in Boulder, Colorado, and we're not as sophisticated as you people here are in New Haven. So it turns out, here, I'll just, here. So this is me. Carl Leinberger is the captain of the negative ions, the smartest guy in the world about doing negative ion spectroscopy. Chuck Depew is a Yale PhD, is a member of the National Academy of Sciences. He's an organic chemist in Boulder. Eldon Ferguson is the inventor of the flowing afterglow, is at NOAA, the National Oceanic and Atmospheric Administration in Boulder. This is Steve Leone, who's one of the most famous chemical physicists in the United States and is now at Berkeley. He is the head of the chemical dynamics beamline out there. Zdenek Herman was a postdoc here in the 1960s, and he's at the Academy of Sciences in Prague. And this is Ronnie Bierbaum, who's the master of negative ion chemistry. So I've given you about 10 minutes early, so I'm happy to answer any questions that you people may have.
Okay, so you have some questions or comments? Okay, I have one. So let's go back to your, how do we get out of here?
Oh, you hit a B? Blank.
Okay, but I want to go back to the beginning. So we just, let's, for what it's worth, let's, whoa.
Yeah, so now you could go down and
Okay,
hit
here
this
we go.
square.
I could go up here too.
Sure.
That spectrum you showed that had vibrational, this thing here.
That's right.
Let's get it on.
Yes, there it is.
Okay, there. Now, did people understand how this was working? Right, that you put the laser energy in, and you measure how much of it. So you were measuring this difference, right?
That's right. Yes.
But sometimes some of the energy went into vibration of the molecule, so the energy that came out was smaller to the extent that vibration energy went into the molecule.
Right.
So here you say is when no vibrational energy goes
That's
into
correct.
The,
That's
goes
correct.
into the product. Okay?
Right.
So that's how you know what the lowest energy.
Sure.
But here's a peak here.
Right. So that comes from the fact that you have a vibrationally excited negative ion. The negative ion, instead of being in its ground vibrational state, has a little bit of energy, and it'll actually be in the CO stretch is where this will be. So if there's energy in that, in the negative ion, then to go back to our diagram, I've got to go here. If you have hot bands, in other words, if you have some of the molecules have vibrational energy in this, then the molecules aren't down here in V equals to 0, but they're actually populated in higher states here. So that means that those electrons will take less kinetic energy to get off. And you can always spot them because they'll have a different frequency. Here. The frequency different. You're going to have a set of frequencies here, which will be a mode in the neutral molecule. This is the methoxy radical, and this is that of the negative ion. And so this is the vibration in the negative ion, and they'll be different because the electrons are different in these things. So you can guess when you get to a molecule which gets to be more complex, like phenoxy radical. I talked to you about that. Phenoxy radical has a lot more atoms, so analyzing this steadily gets more and more difficult. But we like to do that. That's what God put us on this earth for. You can also guess, as he showed you what I'm interested in right now in sugars, because I'm interested in how biomass decomposes. You remember, we know what glucose looks like? Glucose is a molecule that has many different hydroxyls on it, and the hydroxyls are all slightly different. So now, instead of making a negative ion like in methoxy, I mean, how hard can this be? You only got one OH. What happens if you have ethylene glycol, or if you take glycerol? Ethylene glycol has 2 hydroxyls, glycerol has 3, threose is going to have 4, ribose is going to have 5. So now you're going to have to begin to tell which OH this came from. So this is going to be a bitch. But if you can do this, you would be able to take these molecules and you'll be able to break all the bonds in them in an order that in the order that you'd like to do it. And that's very interesting to do.
So you were very kind to speak about putting electrons into sigma star orbitals, and you don't believe in sigma star orbitals. I believe. Professor Ellison is not a big fan of molecular orbitals. My favorite.
Yes, that is true. Look, I do valence bond work, and this is a matter of taste. There's different ways to view these things, and in the end, the only thing that counts is what you measure. If you have a model that can account for what the patterns that you've measured, and you can predict what the next values are going to be, you understand this. But it's the data that what survives. The rest of it is all a matter of opinion. He likes sigma star orbitals. I don't.
Okay, you were talking about the stability of the phenoxy radical in terms of its resonance stabilization.
Yes.
So I think these people could help you out with that, or at least point out something interesting.
All right.
You say that this radical is stable because you can draw resonance structures that have, you like
yes,
resonance structures
that's right.
and so on, okay?
Correct.
But how about if you say that in the starting phenol, that's the bond that you're going to
Sure.
break in here, right? Here I got a pair of electrons
Yep.
that I can draw resonance structures for.
Sure.
And so on. So it looks to me like it's worth more here than it is
Listen, dream on, big boy. Look, here. How do I push this thing up? How do I push this? How do I get this thing up?
here. Okay, we'll get that.
Here. Here. So this electron is going to get delocalized over the whole molecule. If you try to do this with an electron pair, what you're going to have is okay. So if I do that, I'm pushing charges around. I don't like that. Okay, here. I don't like the fact that the oxygen's going to have you're starting to suck electrons. You're starting to, as the electrons migrate down, the oxygen is going to become positively charged. So, geez, I just would never do that. But what's true is that bond energy, honest to God, really and truly, is 86 kcal per mole. Yep. That is a fact. and this is a flippant way to have anticipated this. Contrast that with, say, here, methoxy dot. Where's that electron going to go? It's literally stapled to the oxygen atom. There's nothing it can do. It can't go anywhere. So when you break that bond to get hydrogen atom, you get the dot that just stuck right there. As you pull this bond off, the dot now is able to be delocalized and spread around the whole ring, and that's and this bond energy then in phenol, this bond energy that's going to be 86 kcal per mole. This thing lets you measure the absolute heat of formation of 298 of this thing, and that has this low bond energy is going to mean that this heat of formation is going to be low. So what that means is if we're trying to study lignin, and lignin are trees, Okay, you know, you take a chainsaw and you're cutting trees down. That's very tough material, and all these compounds are long three-dimensional polymers of aryl alkyl ethers. So, if you know the heat of formation of phenoxy radical, this bond turns out to be 62 kcal per mole, and if you do this in this, it's like 90, and that's 1.5 volts. So when you heat this, all these molecules break apart, and the first thing they do is they form phenoxy radicals, and this triggers a decomposition of these things. So it turns out I don't like these things in the neutral molecule being delocalized, because I think you have to separate charge, and I don't like that.
There are actually people back here who are smart about this kind of stuff. Do you guys buy that?
You. No. Here. What's the case?
What I'm thinking is, if you have that kind of, you think there'd be a spin observable.
Oh, indeed there is. If you look at the EPR spectrum of this radical, it is delocalized all over the place. And here, I mean, you're an expert in this. You know about all these hyperfine couplings and whatnot.
You see coupling from the protons around here. It's like NMR. So if the electron spin gets out on these protons, then it interacts with the nucleus, even if the molecule's tumbling, right? You don't have to worry about the anisotropy.
Yeah.
So it's no doubt it gets delocalized, but why doesn't this one? So Barney says it's because he doesn't like
charge.
He doesn't like to separate charge and resonance structures. But that's not, is this Coulomb's law or what? Anybody got an idea back there?
Well, here, we say, what do you mean is this Coulomb's law? Coulomb's law is what it is. Okay, here, no, okay, so here, so here, if you want to draw, if resonance forms like this are important, then that means that I think as a consequence of this, you have to have charge separation. I think these are high energy resonance forms. If they're high energy resonance forms, they don't contribute to the superposition of the wave function, is the way I say that.
That's because you believe in resonance.
Well, okay, because I'm a valence bond guy. Okay, but what's true is this 86 kcal per mole.
Yeah.
Nothing could be done about that. Okay.
Okay, I think